So my name's Condron. I've been building message-oriented and distributed systems since the mid-90s. I started in telecom right when we switched over from analog circuits into packet switches and the big switches, voice over IP. And then from there I've moved into insurance and finance and done some work in biotech. And got my, I went to training with Greg, took the CURS course about, about 10 years ago, and everything just sort of clicked with me. And so one of the things that I've heard time and time again is this. Everybody knows this is true, right? Once you're distributed, once you don't have one database on a local machine, running one thread, things are hard, right? And my thought was always, I'm not getting something. Because for me, it always seemed really straightforward. And generally when that happens, that means I don't get it, right? Because if everybody knows something and you don't agree with it, most times that means you're missing something, right? And so I thought about it for a long time. I was like, maybe it's my experience in the telecom industry that made me think that, why isn't this hard? Why does this seem to be straightforward when everyone has all these problems with it? And as I was thinking it through, I remember thinking that chess was hard. So I learned chess when I was a kid. My parents taught me how to play, right? And it was all about the chess master, Kasparov, staring at the board, deeply understanding everything, right? And then I got to college. And in college, I met some of these guys. Now this is Union Square in New York City, and these guys, for 20 bucks, will play a game of chess against you. And I bet you almost everyone in this room, myself included, they're gonna beat you, right? And they play fast, and they play really well. And I learned from one of these guys how to play chess, and not only how to play chess, but how to teach chess. And I actually became a professional chess instructor. We ran a club, we taught at-risk children, right? And our message is, chess is easy and you already know how to do it. And in 1 to 2 hours, I can get anybody to be able to play a good, solid game of chess against anyone, feel like they know what they're doing. It's not gonna make you a master overnight, but it takes all that mystery away and gives you an understanding of the fundamentals to get started, play well, and grow to wherever you want to go. And here's the master secret, right? You divide a chess game into 3 areas: the opening, middle game, end game. In each one of those areas, you've got 3 goals. In the opening, don't run around figuring out what to do. Control the center. Develop your bishops and your knights. Castle your king. That's it. When you're done with that, you're done with the opening. Move on to the mid game. In the mid game, you want to open a file. You want to get across the board to the other side. Get the major pieces out. Hook up your rooks. Get the queen out there. Set up a battery. Go for the gusto. Right? And in the mid game, you want to pick an area. Are you going through the center, king side, queen side? Focus your efforts on an area of the board. Then, once you've gotten an advantage, you're in the end game. Trade down. If you're up 1 piece and everything's on the board, that doesn't matter. But if you're up 1 piece and it's a king and 3 pawns, now that matters. So trade down. And in the end game, it's all about getting your pawns across the board. And this is the time to take your king out from the castle and go on the assault, right? And then you need some general skills, right? Don't waste time. You know, if you can do 2 things with 1 move, you're ahead on time. If you move a piece twice to get someplace, you're behind on time. Practice your combinations and learn your pawn structures. If you do that, you can sit down with anyone and not get, you know, a fool's mate or a scholar's or feel like you don't know what you're doing. You've got a plan, you got a simple set of rules, and you know how to approach the game. So when we talk about doing real-world message-based, event-sourced, distributed systems, distributed systems are easy, and you already know most of it, right? So we're going to break this down into a couple of key patterns and a couple of key resources you're probably going to look to go get rather than write yourself. And once you have those, you can combine them to solve all of the hard problems in distributed systems, right? Because just like chess, a lot of times when we're looking at distributed systems, we're like, oh, well, how do I deal with a distributed transaction between an event source system and my database? Or what if the message doesn't get there? And, well, what if I have a stream message and the one in the middle is missing? How do I deal with that? Oh, wait, I've got to build something that's idempotent, right? How do I deal with all these different questions? Sort of plagues and dogs us. And the truth is, with a couple of simple patterns, for most cases, there are some exceptions, this will give you reliable, scalable, working systems in production. So let's take a look at what those are. And one of the things I have done here, because I've found that there is a wealth, a ginormous list of conflicting terminology, I've tried to boil everything down here to the most basic names I could come up with, right? You need some sort of data store, right? It's got to be able to have name collections, you know, an AK stream, an incrementing index, and it has to have distributed consensus. That's one of the big key things here is, for most people, don't try and build your own Paxos. Don't try and build Raft. A SQL Server cluster, properly configured, with an auto-incrementing index on the table that you restrict your access to insert and read, will work just fine. So if you can create a table, insert records, read records, SQL Server, you're done. You don't need anything special. There's lots of ways to achieve this. But that incrementing index and the distributed consensus are one of the foundations of what we're going to build everything else on. Message delivery. Again, just about anything will do, right? You just need a way to get the messages between your different systems. If it's all on one machine, that can be in memory. If you're distributed, you use something like 0MQ. It does not need to be a persisted, brokered kind of system. You don't need any guarantees on delivery from your messaging system. All you need to do is be able to publish on topics and subscribe to things. That's it. Messages need to have a key, right? There's lots of systems give you a nice, good, global unique identifier that you can slap on every message. It's going to be really useful. And read-only data fields. We just want a little datagram here, a little data transfer object. The next thing, you're probably going to build these things on the right. An appender. So oftentimes this is your aggregate root or whatever, but all you want is some piece of code that can write to a single stream in a way where it can check the version when it started, and it can check the version when it commits. And if that doesn't work, it's gonna throw up. right? And that's going to be the base of your aggregate roots. If you need to do any persisted, Saga or process managers, that's how you commit. Oftentimes, these are called aggregate roots because people talk about domain-driven design in these systems. You don't need to do any domain-driven design to these kind of systems. Now, the caveat there is that domain-driven design is one of the best ways to figure out what your transaction boundaries should be. Because this appender and those streams are the boundary of your transactions. You can't commit across two streams. You want to commit to one stream at a time. And domain-driven design will help you figure that out. We're also going to need to build message queues. These are going to be really, really simple. Take a message in, have one of many different ways of spinning them back out, either directly to a handler or just republishing them. They need to be able to subscribe and dequeue in order. And we're going to use these for organizing our message streams to things and for managing our system performance, throughput, and production operations. Right? A coordinator. This, the simplest name I could come up with, because as soon as you start talking about sagas, process managers, all these things, everybody loses their minds. All this is one thing. It's a message-driven state machine that lets you coordinate between two different systems without needing a distributed transaction. And the last one here, scheduled message delivery. This gives you time. And it does it in a way that's message-based and not on a local clock, because you can't trust any of your local clocks once you distribute it. Generally, what you're going to do is you're going to send it a message in an envelope and say, wait 5 milliseconds and send it back to me. Wait 30 milliseconds, send it back to me, or send it to me at midnight. And we're going to use this to trigger all of that asynchronous behavior in the system. So let's talk through each one of these in a little bit more detail. The data store. Doesn't matter really what it is, but the key thing here is that your base transaction scope, what you can commit, is the stream. All right? So you have to realign your thoughts. One of the things I don't like about relational databases, and I've used them and I've built systems on them for decades, but it has occurred to me that we build these third normal form schemas with this sense of magic consistency across everything, right? One of the best examples I've got is when you're trying to figure out how to do something along the lines of, I was working for a financial institution and we needed to say, when the business makes the decision that this company is trading in blood diamonds, you can no longer trade with them. It violates our corporate ethics, and you're done. Now, if we build that in a classic system, we're going to update that table, and then the whole system will be consistent, and nobody can trade on that. But what about all the traders that already hold it? They weren't told before the meeting that they weren't going to be able to trade this, right? Someone up on the 30th floor sat in a conference room, made a decision, right? So you could have orders in play, you could have orders placed after the decision. They're all valid, right? And what we do actually, when we have this magic thinking about everything is perfectly consistent, we don't walk through, well, how do we unwind it? Is it okay for that purchase order to complete? Do we have to unwind that right now? Things happen in series. And so by saying that the stream is our scope of a transaction, that's as far as we're going to let be consistent, it forces us to think through all these problems and model what's really going on and have better conversations with the business. That's the other benefit of that ubiquitous language in domain-driven design. But again, it's very useful, definitely not required. The other huge thing here is building a vector clock on each stream. So just having that auto-incrementing index that says we're going to append things and we're going to know where things are solves a tremendous number of problems. You want to take a stream of messages, and I want to know I got them all into my database. Because when I build this system, I'm probably going to have a SQL Server database someplace, summing things up, creating read reports, synchronizing with my event system, especially if I'm adding it onto something existing. How do I do that? Well, if I know I'm only appending, and I know I've got a sequence number, and I know they're all in order, then I can say, well, if I see 1, 3, wait a second, where's 2? I have a very simple rule to detect missing messages. I know that my cache invalidation can be infinite because I'm never going to let you go back and rewrite the data. So I know that that cached information can live forever. So that means I'm not going back and rebuilding everything I turn on. It's like, I've got this view, I've got this table, it's at position 50. If I get events 51, 52, 53, I just add them. I don't go back and rerun everything. So all of a sudden the synchronization problems become very easy. Now, that means I can be stale, but I'm not going to be wrong. And stale is a question of an SLA. It's a conversation you have with the business. You say, well, you know what? I can have you 1 millisecond stale at all times around the world, but we can't update the system, ever. Or it's going to cost you $1 billion. Or is it okay if it takes a quarter second to get there? And they're like, am I even going to see that? Right? So the other thing is that once you've got your base streams together, like I've got a stream for every user, I can have all of my users' positions aggregated into a master level user stream that just has a vector clock on the total set of users. So now if I want to know if I have any new changes to users, I have another position I can use. And that stream doesn't need to have all the data in it. It's just all the positions from the user streams, right? So it's a projection, it's a projected stream that has the master position for the entire category. The next big thing we're going to use is queues. And queues are going to do two different things for us. So the first thing is, when you build out a system and you're setting up your routers and your topics and everything, if you've got a set of operations that you know all apply to one area of the system that need to be in a particular order, run them through a queue, and the queue is going to provide a guaranteed ordering of all those things. It'll give you a guaranteed winner. So then you can have a single-threaded operation off the back end of that queue that will process them all in a given order. So you don't have to worry about different things happening at once for parts of the system that need that ordering. But for most of the system, what you want to do is you want to divide things up so your transaction boundaries don't require you to do this, right? You're only going to do this in those areas where you have a problem. The other thing that you're going to use this for is if you put a queue in front of every processing element in your system, you can then pull that queue or have the queue alert on its queue depth. How backed up is it? How fast are things going through? So if I have an auto-scaling group, and I've got a queue in front of the auto-scaling group, and all of a sudden I start to see that queue rising, I'm going to just spin up another node, fan out to one more. If I'm seeing that queue sitting there empty, I've got no handling time, no busy time, and I'm running 15 nodes, I'm probably going to scale that down and recover those resources. And it gives you a simple, consistent way you write once and use throughout the entire system to manage that. And you've abstracted it, so you can use that same queue process to spin up a new thread in a local system, spin up a new Docker container, whatever you need to do. You can also, as you apply load, watch the queue metrics as that load passes through your system. And you'll be able to tune your entire system by adjusting the number of handlers to get total throughput on your system. Right? So as you're like, how do I set this up? How do I monitor production? These queues tell you where the bottlenecks are. Now, one thing I'll tell you for free is as soon as you fix one bottleneck, you're going to have it move to another place. And so it's a matter of adjusting all of your bottlenecks for end-to-end throughput. You need to have your SLAs be for the end-to-end transaction through the system, then use the queues to tune that. And again, you're probably going to have different types of queues that are either doing a simple republish, because all we're trying to do is measure depth or reorder, round robin, single threaded, lots of different ways to make these all work. But it's just bring it in a queue, have handlers at the bottom that round robin it out. Appender. This is where we really set that stream context. We go through and we say, okay, this is my transaction. And one of the things we've got to really work through here is getting rid of that mentality of we have one unified state. Because we have append-only data, we don't have to worry about a lot of the referential integrity things that we're used to dealing with. Once a key exists that has been put in the system at a certain position, that key is always going to exist. Now the key might eventually get another event that says it's deactivated, and we have to handle that. But we don't have to worry about these primary foreign key updates on insert. On this user, I'm doing these actions. That user will have always existed. The user may leave the system. We may delete all their personal data, but that user ID will always be valid. You know, unknown user 592 will have always existed even after GDPR has pulled all of their information back out. So our system isn't going to be corrupted. We just need to think through that use case of what do we do when we have users who have opted back out? How does the system deal with that in the metrics? So then the appender is going to be able to get the current state, optionally do an idempotency check because we've got our message ID before. So if we write into the stream the ID of any message that we've processed, we can very quickly and easily check, hey, have I done this? So that whole, how do I get at least once delivery, how do I make it idempotent? For live updates, this is a very simple way to make sure I'm not processing things more than once. Do the work. Now, because we're in a distributed system, because we might be running hot, we need to recheck with the store when we commit to say, did the world change underneath me as I was doing the work? So by doing this simple operation, find out my current state, do my work, and then check the state as I commit, I know I've got sequential appends, and I know that multiple updaters can't corrupt the state of the stream. One's always going to win, one's always going to lose. Now, when we lose, there are a couple of different options. I'm going to jump down here, I'll come back up. The coordinator, this process manager, a command, a saga, one of the things we're talking about here is a very simple little tiny state machine. And let's take the example of a command that we were just talking about. I send a message, right? When I've got a handler, I make my appender acknowledge receipt of commands because I want it to participate in this coordinated activity. We subscribe to that acknowledgement. We subscribe to a timeout. We send the message, and then we send the timeout in an envelope. And then we just go to sleep. And we have the system wake us up when we get either an ACK, which can be success or failure, when we get a timeout, right? And so if we get the timeout after we've gotten the ACK, we just throw it away. We don't care. We just take this little object and throw it away. It's probably a little 5-line state machine, right? But this allows us to decide what we want to do when that command fails to commit. Do we just resend it? Maybe it's still valid, right? Maybe it's okay that we can just retry. Do we have to alert the user? So in the publisher, we now have this option. So our publishers maybe is our UI. Do we pop an alert saying, sorry, someone edited that record? Do we attempt to seamlessly retry it? Now, without having a distributed transaction, we've got a simple way to know whether or not something's been achieved. Now, as you get into more complicated scenarios, you might want to add time to life, different things to these messages for things that get really stuck and stale. But for most cases, this is going to solve everything you need. And this is the heart of what a process manager is. In most process managers, it's going to be longer lived, and you might be handling coordination between 5 or 6 different things. And that state machine's going to get more complicated. But it all comes down to this base case and then expanding upon that. Do we have a question up here? Depends on your system. I mean, that's rolling back an infrastructure change is completely dependent on your system. I don't quite see. I can tell you how to do that, but I can't answer the question of when or what should trigger it. All right. Scheduled to miss message delivery. I like to call this, when I build them, a later service. Just send me this later. If you saw the talk yesterday about injecting time into systems, right? This is the same thing. So it's either an on-demand, hey, let me know when I've expired, when do my timeouts happen, how do I externalize time in the entire system, or how do I pulse time into everything on a certain heartbeat? Because remember, one of the things I said before is, in this approach, we know that we're not invalid. The worst we can be is stale. How do we know how stale we can be is based on time and SLAs. This service allows us to send heartbeats out, say, are you in sync? Right? So now all I have to do is send out a heartbeat saying, are you even with the most recent position in the stream that you're watching? So now I can do a proactive functional push to the system that I'm dealing with rather than trying to somehow coordinate in real time. So those are the things. I didn't bother talking about messages or other messages because I think those are pretty agnostic in any type of system. There's nothing, there about it. But the key things are your data store, SQL Server, Oracle, DynamoDB, Event Store, whatever you want to use. The key is make sure it has good distributed consensus and failover properties because you're depending on that. And it's got the ability to do the incremental index and restrict updates. And a simple appender, a message queue to order any things that you need to order, streams to read out your vector clocks, coordinators to distribute things, and a later service to deal with time. The other great thing about the later service is in your unit tests, you can send timeouts immediately. So you're not dealing with sleeps and waits and things. You just say, do this, fire the timeout. Bang. And we know the behavior is as we expect. So, eventual consistency message ordering. The first thing that I think we need to do, and you're going to see on most of these, that half of the answers are it doesn't matter, right? We generally get too caught up in the edge cases where it does matter, right? If I'm dealing with a system that's just doing a live wash of data, like if when I was writing video streaming systems, if we missed a frame, we dropped it. You don't go back and try and get a missing frame into a video stream. You just keep moving forward, right? There are a large number of systems where it doesn't matter what order your friends liked your post in, right? You know, there's things where when everybody that finishes the marathon gets a medal. All I care is everybody finished. There's other things, like the Olympics, where the person that came in first, second, and third really care about the order they stand on the podium with a gold, silver, and bronze medal. If it does matter, run the topic through a queue to guarantee your ordering for live message traffic streaming into the system. You've got commands coming in, and we need to know what order they happened in. That queue gives you that guaranteed ordering. First one wins in the queue. And then the second one is on the output side, and then you're going to commit to a stream, and you're going to use that vector clock in your stream position. And that could either be for a low-level stream or an aggregated high-category stream to be able to get that position back out. Missing messages. You know, what happens if one of the messages in transit gets lost? How do I deal with this? If I'm reading from the data store or I'm updating, just use the stream index. That's why we put it on there. So if I see all the messages and I miss one, just stop, go back and ask for that message. Hey, I need message number 53. And then keep processing. All right? And then with published messages, missing messages are about things that need to be handled. That's a situation to use a command, to use a coordinator. So all you do is take your coordinator and say, if I don't get an ACK back that says this was done by this timeout, resend it, retry, whatever you need to do. You combine that with the idempotency that you already have in your appender, and you can safely retry commands. Distributed transactions, again, for live messages, use a coordinator. For stored data, and this is the case where we're taking one storage system and updating it from another, leverage the vector clock, right? If as soon as you write that vector clock into your target system, you know your position, you know where you're at, you can always recover. The other thing that I always hear all the time that people are worried about is, well, if I have a million events, how do I replay them? What about the data size? What's going on? And the answer here is you can cache what's going on. You don't need to go back and replay from the beginning of time. Because it's write-only, just take where you're at and move forward. You can do this in memory with your aggregates. You can do this with your in-memory read models. You can do this with your tables in your database. You're only going to have to deal with the new events. And once you've transformed them to whatever reporting format, table format, read model you need, you always know that as of that position, you're always good. And that's the last thing is your cache invalidation time is now infinite. It's as long as you want to keep the data around. Cache eviction is different. You may want to evict things, but it's never going to go bad. Guaranteed delivery. Handling things that I've published throughout the system. There's a lot of times where you don't need to know, you don't care, you want to have new subscribers coming onto the system that you don't know about. In those cases, the publisher doesn't care, doesn't know who's consuming these live events, and that's just fine, right? It's the consumer's responsibility to know and be subscribed to what's published, not the publisher's responsibility. The other thing, though, is sometimes you need not just live updates, but stored data. If you need to be able to go back and look at this stream in history, then commit it to the data store. Put it in a stream. One of the examples here to pull again from finance is live market prices you don't store on disk. They're always changing, it doesn't really matter. But you will take a snapshot every 5, 10, 15 minutes, store those on disk, just because of the data volume, right? But again, this is, I don't care who wants to look at, who wants to read these prices. I'm just saying, here are the prices, they're available, go look at them at this timestamp whenever you want. Here's the whole history of price changes. If you do have to handle it, go back and use your coordinator. So I hope you guys are seeing the theme here. These, I've tried to boil this down, I've tried to write the shorter letter, take a little bit more time, and say, all you have to master is 7 things, and we just recombine them to solve all of these problems, and make a whole category of them just go away, then solve the rest with simple recombinations of the same thing. Idempotency. If you're processing saved data, just use your stream position. This stream at this position is always unique, can always be repeated, it's never going to change. So if I get user number 592 position 3 as an update, it's always going to be the same thing. If I've already seen it, throw it away. I don't care, right? Generally, you can actually optimize that. If I've seen every event of this user up to any position, anything before that, I can safely ignore. Only things after that position do I need to worry about. Handling messages, this is one of the reasons why you put the unique ID on all the messages. That unique ID allows us to do a number of really cool things. Idempotency is one of them. Because I have a unique ID for every message, in a situation where I'm doing live transaction processing, if I just keep a simple hash of the IDs I've processed, I can check that before processing and then know whether or not I've handled it. Now, obviously, as system volume goes up, this can get problematic. So you want to make sure you have, a time to life, you have some handle around keeping that hash from getting too big in large systems. This comes down to understanding the scope of your trafficking and where your targets are going. So you're not dealing with too many things at once. So this is where, we'll get you to be able to play chess, but we're not going to make you a grandmaster overnight. This is going to get you on the board, get you playing. So this ran a little bit faster than I was expecting. But my advice right now is just go build a simple distributed system. You can build effectively a distributed system on your machine using threads to process everything independently. There's no difference in an isolated system between running on multiple threads you're dynamically creating and destroying that communicate via messaging and something that's out there using, AWS. The logical problems you're dealing with are exactly the same when you don't have interaction between your different processing components. So, questions? Did this all make sense, or am I just crazy? Because mostly it's the second answer, that I'm just crazy. Yes? Sure. Yep. So the idea behind the later service is you set up, generally you want to use something persistent, because this is going to be fairly important in your system, something with some redundancy, that accepts a message envelope that's going to have on it either a scheduled time to send, or it's going to have a delay. So what you're going to do is you're going to convert the delay to an absolute time, have a stack with all your absolute times in it, insert the message into that bucket. So generally what I've done is I'll have an index of the next, 10,000 milliseconds, each one of those with a bucket with messages in it to send. I just go get a set of those, read through all the messages to send, push them all out, come back and do that again. So you've got one thread updating the queue, another thread watching it and sending it out, and it just goes to sleep until it gets the next time to send. Now, patterns you can use doing this is timeouts and message handling. This command must be handled before X. Hey, every midnight we need to do this processing. So the service that does that says, processes at midnight. When that event gets fired, the first thing it does is set the next event to process at midnight again, then go through. So this allows you triggers in all sorts of parts of the system. The other way you can do it is you can have a heartbeat clock that says every X amount of time, tell everybody here's the current time. Now that requires you, that's a more advanced pattern, and that's going to have all your messages with effective times and processing times to look at the system state. Once you get the base pattern down, you can then go look at that fully temporal processing model. There was another hand over here, I thought. Yes, no, lost it. Okay. Okay, so if you never delete things from the store, how do you deal with storage growth? Okay, so there's two things I want to talk about this. Every time I've built a real-world production system in a database, relational database, there's the primary schema everybody thinks about. It's third normal form, it's optimized, it's nice and small, and then there's the first normal form reporting schema that you make, and then there's the audit schema, and then there's the history schema, and those all now double and grow and get bigger and bigger and bigger. So what I found in practice is that event source data storage is smaller on the ground than relational data storage in any real world system. Because I'm not doing these two-phase commits every time I update the third normal form of my tight schema. I also have an audit record, and I add one of those for every single change. And it has everything in it. Now, that's one app. But to answer your question much more directly, you need to plan for growth and storage explicitly. So versioning and event source systems, Greg Young wrote a very nice ebook on that in LeanPub. One of the patterns in it is end of year rollups and basically making archiving data an explicit part of your pattern and follow the same thing that's been done in accounting for years. So what you do is you say at the end of the year, you close the books. I have one store that runs for this year. In December, I bring up the new books. I make a snapshot of where I'm at, start everything there, and then I close the books probably a month later, so if I have to do any last minute changes, do an update into the new store, and then the SLA for that legacy store is now different from the live data. It's still there, it's still readable, you can audit operations on it, the old UI works, but now I'm not trying to make this event or this data model from 10 years ago, either have to edit it or have to keep the screen always being able to read it. Because what you'll find most times is the SLA, the business uses for that archive data are very different from the live data. And so you just start planning this snapshot and roll out. And you align it with your business cycles. Does that give you a full answer? Okay, good. Other questions? Oh, I should just read the screen. How to handle multiple edits on the same data record with events. Okay, the second one. How to handle change record edits. Don't. So, CRUD means create, destroy, read, right? Because that's what update is. Update means blow away what you have and put this new data there, right? So what we're going to do in the event source system is, if I say, I start with a company, I'm an employee, I've got my last name, right? Then I get married, and I take my wife's last name, right? What I'm going to do is I'm going to append a name changed event to the stream, right? What that means is that in the record, in the relational database that's behind my UI, I'm going to overwrite the field that has my name in it, because that is a transient data source. The source of record, the event store, is append only. The resolved field of what do I use this name for, what do I call this person, is in the read model that I'm going to be able to modify, change, drop. And we're going to know that my name change came in on December 12th of this year at this time. And all records from before that will have the old name. All records after will have the new name. Because there's a position in the stream where that change occurred. The way you deal with multiple edits is one of two ways. You either say that the event that does the change, these things need to change at once. So all of the fields are in the event, or all of the fields are in the unit of work that you are applying to the stream in the appender. There's no reason why the appender can't handle multiple events before it commits. So I have 5 changes there. Now the rule is when you commit, the record cannot have changed since you started. That's your unit of work. So that's how you apply multiple changes, and that's how you change data. All right? Now, if you need to correct a mistake, you're most likely to use a pattern called a reciprocating event. But that's not required. So the requirement is it's append only, and you can have different data that you want. This also means that you can use your full object-oriented skill set in how you model the data. You don't need to use a relational model for how you do things. The compensating transaction is a really simple pattern. If you deposit $500 in your bank account and your bank writes in $50,000, it's not going to subtract $45,000 from your account. It's going to say negative $50,000 with a remark on it, say we screwed up on this transaction. It's going to have a new transaction with the actual $500 in it. That's a reciprocating transaction, and that's just to make the audit log look neat. Think of it the same way you do git commits, right? Everybody always rebases, nobody merges, right? Half the people say yes, half the people hate me. Is that how that? So it's the same kind of thing you do in source control. Any more questions, either here or up on the screen? show of hands, who thinks they could go and build a distributed system, a simple one now? Everybody, come on, everybody, raise your hand. All right, thank you very much, and have a great conference.